Come on in, everyone. Anybody have any questions before we get started? Looks like everybody's here. Well, at least most of you are here.
Hey, Mr. Younger.
Yes.
So I was trying to do the chapter practice on Canvas, but it was locked.
Okay, let me fix that for you right now. I'm going through
And I
this.
was looking through and it was like chapter 5, 6, 7, and 8. The practices, all of them were locked.
Gotcha.
So just for future notice, yeah.
Appreciate that. I'll go ahead and do all of them right after this tonight, but right now I'm going to go ahead and you said the chapter one, the one that you were doing was 5.
Yeah, 5 and yeah.
Hopefully what's wrong with it. Let me look at it. Yeah, it looks like I just had a date from the previous semester. I'm slowly taking all those dates off. I thought I had done this class already, but I did one this morning, and it was, of course, a different class. But anyways, that 5 is now open, and it appears to be working. So when I'm done here, I'll go ahead and do the same thing with chapter 6. And it looks like 3 and 4 might have been that way as well, but that was back in May. So, of course, that was before y'all had class, and no one should have got a chance to do it. But it'll be fixed. Okay, 5 is fixed right now, but the rest will be fixed. Thanks, Logan.
Okay,
Anybody
thank you.
else have any questions? You're welcome. All right, so last time we talked about gravity, and I want to get you guys started, or actually want to show you a couple more problems with that scenario. But I also want to get you started on the next chapter, which is chapter 7, which is about conservation of energy. And I'm going to give you a sort of short intro to that actually gives you everything you need, so you can literally do every one of the chapter problems for chapter 7 all after this one example. But I still plan on covering another day with you. So let me go ahead and share my screen with you guys. Again, if you have any questions before I'm getting up and rolling and everything, make sure you go ahead and ask me. Another student came in. There it is. Okay. Let me move this out of the way a little bit. And let me turn on my chat so I can see that. Evidently it will not. Let me turn on my chat. There it is. Now I got a chat window open in case anybody chats anything with me. So I wanted to let you know, we basically started off with me telling you about Newton's law of gravity. If you use the 27.3 days, by the way, you can actually get that mv squared, or excuse me, that v squared over r is the 0.00272 for the acceleration. And that's the same thing as you get when you divide 980 by 3600. That was one of the problems that I normally do as a problem as the chapter opener. Your book actually did it. It's fine. So you don't need to see it. I just want to let you know there's multiple periods you can talk about with regards to the moon, and it depends on which one you use, obviously. But the distance, or I should say the time period between a new moon and another new moon is like 29 and a half days, 29.5 something. Whereas the time required for the one orbit of the Earth relative to the distant stars, that's 27.3 days. And that was the one I used. Of course, you got to convert it to seconds. But anyways, that's it. Now, I wanted to go ahead and talk about what Newton's law of gravity allowed us to understand about Kepler's laws. So I need to cover Kepler's laws. So let's start off with Kepler's laws. So what's going on here is around the time, and this is Kepler's laws of planetary motion, around the time of Kepler postulating his rules, what's going on is that he's taken a job with a guy by the name of Tycho Brahe. Tycho Brahe, I told you, was a guy that got his own nose cut off in a duel over who was a better mathematician. And he's got really great data, and it's mostly as a result of him because he's just a really good experimental astronomy observer. And Kepler knows that he's that good. In fact, Kepler has a chance to stick to his guns and keep a particular model alive, or come up with an all new one. And basically, he erred on the side of Tycho Brahe's data being great. And because of that, he ended up postulating his laws, which turned out to be essentially correct. I mean, the laws that he found are what we call epistemological. So they're just based on data. There's no underlying theory of why it's so. It's just, this is what I've observed. These are the rules that I think I can apply. And these are the rules I think you should apply if you're going to make any future predictions about the planets. So his first one is one, the planets orbit the sun in elliptical orbits with the sun at one focal point. So I'm going to draw that for you to some extent, so you can see what we mean by that. So that is sort of an ellipse, and the way you would go about drawing an ellipse is you would put let's say 2 nails in a board. You know, if you draw a circle, you might want to put a single nail in a board and tie a rope to it, and then tie a pencil to the other end, and then hold the pencil perfectly upright, keep the string taut, and circle around, and that'll make a circle. Well, if you want to make a ellipse, what you do is you put 2 nails and then you tie a rope to them, and the rope has to be a little bit longer, as a bare minimum, a little bit longer than the distance between the nails. And then you pull it taut and you stretch it out like that, and just go around keeping the pin vertical and keeping the string taut and that sort of thing, and you'll sweep out an ellipse. It's helpful to know the parts of the ellipse, so I'm going to go ahead and show you that now. Oops, I did not mean to do that, but here we are. Okay, it's pretty good. All right, so now I'm going to take and tell you some stuff. So this distance from end to end is called the major. The object is called the major axis. And we also use more or less the same word for the distance. But in fact, the distance isn't that important, but the half of the distance is kind of important. So we do use that a lot. And as I said, this is called the major axis, and we would say length equals 2s. And I'm getting ready to show you what s is. So you're just imagining here, basically starting from this point, going through the 2 focal points and ending up at the farthest point. In other words, we're measuring the largest distance across the ellipse, and that distance is called the major axis. The semi-major axis is really from the center, which we would say is right along here somewhere, down to here. That's called the minor axis. And what that means is the semi-major axis, S, is basically the distance from the middle to that end. And there's a reason I'm explaining all this, so just bear with me for a second. That also means that S is the distance from the middle to this other end, okay? So that's the semi-major axis. And in fact, this little distance right here is E times S, where E is the eccentricity. So the eccentricity of an ellipse is actually equal to, there's a couple ways you can look at it. you can say basically it's 2ES. In other words, it's the total distance from one nail to the other divided by 2S. So in other words, it's the distance between the focal points divided by the total distance across the ellipse. So this is F to F, and this is what we call perihelion to aphelion. So again, the first law says that the planets orbit in elliptical orbits with the sun at one focal point. So you can imagine, for instance, maybe the sun. Let's see if I can get another better color that I like here. I'm not really impressed with this color selection. I'll do this one. Oh, that's going to do terrible. Okay, I'll do this one. All right, so if you imagine the sun being here, then this position right here is called the planet being at perihelion. And this position right here is called the planet being at aphelion. So here's the whole reason I'm showing you all this. So I've given you the definition of eccentricity. I've shown it to you on here. You can see, of course, from the definition I gave you, that it's also equal to just basically the distance between the focal points, or distance from center to a focus, which is where the nails are, divided by the semi-major axis. Okay, so you can do it that way as well, which you can see is the same thing as the other formula, but that's the eccentricity. That's how you can find the focal length given the semi-major axis. You just multiply the eccentricity by it. And you can also see from this that the eccentricity equals 0 for a circle, which a circle is just a special case of an ellipse. And for instance, the orbit of the Earth has an eccentricity of 0.017. So it's really close to a circle. In fact, the most elliptical of the orbits is probably Pluto's, even though that's not considered a planet anymore. And it's still only, I think, on the order of 0.02 or 0.03, something like that. So not very big. Again, that should say a lot to you about Kepler and what he was able to accomplish with Brahe's excellent data as well. He was able to discern a very small difference in the orbits being elliptical as opposed to circular. Okay. Now, if you think about the average distance that the sun has between the sun and the planet, you might think of doing some calculus and calculating the length at every individual arc and doing something like that. That's really complicated. It can be done, but it's not that helpful. What is also a reasonable way is you can say that the average would be, so let's say average distance. Let's say average orbital distance. Could equal the average of largest. Actually, let me forgot a T there. The average distance would be the average of the largest distance and the smallest distance. Does that sound reasonable? Does that sound like a decent idea of what you might call the average distance between the planet and the sun? Does that sound okay to you guys? So if you look now that you have that idea as an average distance, if you take the distance from the sun to perihelion, let's draw it with a different color here. I think I'm going to go with black. This distance right here to here is called the perihelion distance. And then this distance from here all the way to here would be called the aphelion distance. Okay. But I think by seeing that, you can see that if I add the aphelion and the perihelion distance, what's the total distance that I get? Anyone? So again, let me restate the question because it seems like maybe y'all didn't hear me or didn't understand me, or maybe you're just shy. I don't know. So does the perihelion distance, that thing that goes from the center of the sun to the perihelion position, and the aphelion distance, that thing that goes from the center of the sun to the farthest point in the orbit, do what do those two distances add up to give you?
The major axis?
Exactly, the major axis. Okay. So if I took the average of that, that means I would add pH and AH. Oh, geez. I would add pH plus AH, and then I'd just divide that by 2 because there's only 2 things there. Well, as you said, the pH and the AH do add up, and they add up to give you the major axis, which I called 2S. So, oops. So when you divide 2S by 2, you get just plain S, which is the semi-major axis. So one of the things we often do, especially with Kepler's third law, is we will hide the fact that we're wanting you to use Kepler's third law, not necessarily as a punishment or a trick question or anything like that, but to make sure you understand that the semi-major axis is the same thing as an average distance between the sun and the planet. So we might say something like, if the period of a planet orbiting our sun, or if the period of a comet orbiting our sun is 12 years, then how big is its, or what is the average distance between it and the sun? So what I'm doing is hiding the phrase that I would really prefer to use, which is what's the semi-major axis, but I'm hiding it to further make sure that you understand not only Kepler's third law, but what the terminology means. So the semi-major axis distance is in fact an average distance. So that's why I showed you all that stuff. You won't necessarily need the eccentricity and all that stuff, but it's good to know that, yes, as you approach 0, it's getting to a circle. And when it's exactly 0, it's a circle. As it approaches 1, it becomes more elliptical. And in fact, when you actually get to a 1, it would be just a straight line. So now we've covered Kepler's first law. Kepler's second law says the planets sweep out equal areas in equal time. So the planets sweep out equal areas in equal time is what Kepler's second law of planetary motion says. So I'm going to draw another attempt at an ellipse. I'm letting the computer make it a little better for me, but they're still coming off crooked. That's okay. So now I'm going to take and say this will be the sun at one focal point, of course. And what we can imagine is a line from the center of the sun to the planet on a particular day, and we'll call that day 1. And then again later on day 30. So basically like 29 days passed in there, or maybe if I said day 0, it'd be 30 days. The main thing is, as long as you take a certain number of days. Now I'm going to call this area A1. Now I'm going to draw another line, and I want it in principle to have the exact same area enclosed as that other one is. But notice for this side of the this side of the sun, the axis is way longer. So I have to make it much narrower. This area will be called A2, and I'll call this day 1 and day 30. And A2 is equal to A1. So what that means is when the sun, when this planet is far away from the sun, travels this distance in 29 days. And you can see that's not a very big distance, especially when you look over here and see that this planet travels this distance in 29 days. So it tells you when Kepler's law says the planets sweep out equal areas in equal time, what he's saying is that when the planets are closer to the sun, they go faster, because look how large of a distance it covered in 29 days, and then look how small of a distance it covered in 29 days. So that's Kepler's second law. Does everybody seem to have some understanding of that, what we're talking about? Does it make sense to you anyways? Anybody have any questions about it? All right, now we're going to do the next law, which is Kepler's third law. And this is not unlike the way you're learning to do stuff and have learned to do stuff in 241 lab. Specifically, you try to graph parameters that you know have some relationship to each other. In this case, the period of the orbit and the semi-major axis S, you know they're related. So what you might do is you make an axis like this, and then you try various things to graph. So let's like make this the S, and let's make this the period. And if you graphed the period and the semi-major axis, you would not get a straight line. Okay. So you also try things like the period squared and the, well, I made that a little small. Maybe just do it this way. The period square. Oh, geez. The period, dang it. I hate this thing. The period squared and the period to the 1/2 power and the period cubed, ... And none of those work out with the semi-major axis to the 1 power. So you start trying the semi-major axis to the 2 power, the semi-major axis to the 1/2 power, the semi-major axis to the 1/3 power, the semi-major axis to the 3 power, so on and so forth. None of that works with just the period. Well, what ultimately works is t squared and s cubed. When he plots those, then he gets dots for the planets that looks like this, and a line of best fit gives him that, and he can say all of a sudden, and this is Kepler's third law. Kepler's third law says the square of the period is proportional to the cube of the semi-major axis. Okay. Now, if you have a hard time remembering that, all you have to do is think about where do Americans, or what's the most famous place for Americans to celebrate the New Year? I'll give you a hint. It's up north on the East Coast.
Times Square.
Times Square. Yeah, it's in New York and it's Times Square. And you see that the period is a time and it's squared. So that hopefully helps you. Now, once this is done, eventually it's accepted, everybody immediately sees how much easier it's going to be making the predictions and almanacs and stuff like that for their jobs, because these astrologers, that was their job. They would make almanacs for the government and various other groups, and then those almanacs could be used to plan functions and things like that, because at that time they really didn't know that astrology was a pseudoscience, because they hadn't been through the scientific revolution yet, which is where we learned that a lot of times we fool ourselves with data. And they hadn't learned things like double blind testing and stuff like that, which is extremely, extremely important, especially when you're dealing with people. So they actually believed, hey, if a particular president is going to try to make a peace treaty, and you look and you find out that his birth constellation has the god of war in it, i.e. Mars, then maybe that's not a good day. Okay. Or maybe that's not a good month or something like that. And that's literally what they use to make such decisions at various levels. We've since really shown that there's no real science to astrology, and it's even so bad that any two astrologers you could get could be given the exact same star setup and come up with entirely different predictions. So that's just puts the final nail in the coffin. But with this, we at least had a paradigm that we could use to make these new almanacs, and it was way easier. I showed you, or I mentioned to you, the Ptolemaic model. By the time Copernicus comes along, there's cycles and, epicycles and deferents and equipoints, and I think it ultimately had like 80 some circles and circles on it, or I should say 80 some circles total on it. And then the equipoint, which was sort of the point you had to look at if you wanted the planet to look like it's going at a constant speed, all this crazy stuff. And it was really complicated. And it was amazing that it was able to do anything accurately at all. But that's just purely because all the freedom it had in it. When you have the freedom of adjusting at least in the case other than Mercury and Venus, you have the case of adjusting how rapidly the center of the epicycle can go around the deferent, how big the deferent radius is, how big the epicycle radius is, how big the period of the epicycle is, and then all that kind of stuff. That gives you so much freedom that if you can make it fit the data, it's probably going to fit the data for several years. And that was what was going on, even though it was dead wrong, because it had, of course, a geocentric universe. And again, in this time, which really, to be honest with you, was probably any time before 1915, 1910-ish, we had no idea that there were other galaxies. We didn't know there were other islands of stars. So when we talk about the universe prior to the early 1900s, we literally mean about 6,000 stars that are close to us, and then Mercury, Venus, Earth, Mars. And for them, they had Jupiter and Saturn, but that was it. It wasn't until quite a bit later that we finally got Uranus, and then Neptune, and then Pluto, all of which came from finding problems with the orbits not matching exactly either Kepler's laws or Newton's law of gravity. They had what we call perturbations, or things that caused them to change a little bit. And because of that, they predicted the existence of another planet, and then boom, they look and they find Uranus. And then Uranus has got some problems with its orbit. And again, they find that it's perturbations, and they can make sense of it if there's another planet out farther. So that ended up resulting in us finding Neptune. And then again, the same thing happened with Neptune's orbit and Jupiter's orbit. They had perturbations that ultimately showed us that there might be another planet, and lo and behold, we found Pluto. Okay, so all this has happened numerous times. We now have a lot more than that. We also have objects that are way bigger. I mean, even our moon is bigger than Pluto, but we have objects bigger than Pluto, and they're in orbits in the asteroid belt that we know of. We have other ones that are in the Kuiper belt, and other ones that are in the Oort cloud, all sorts of good stuff. Now, again, Kepler's laws were epistemological, so they really just had a experimental backing, but no meat hanging from the bone, if you will. So Newton comes along and is actually able to use his law of gravity to prove all of these. And in fact, if you have your calculus textbook, I'm pretty certain, I've never seen a calculus textbook that didn't derive Kepler's first, second, and third laws in it. So you could definitely look that up if you wanted. Your book does a little bit with it. I can do a simple version for you, and I will in a few seconds, for Kepler's third law. But really what ultimately calls number one is, it turns out that Newton was able to show that there's only two forces in nature that can create a closed orbit. The forces are 1/r² force, which is what gravity is. Also happens to be what electric force is and what the magnetic force is. But 1/r² is one of the forces that allows closed orbits, meaning an orbit where a planet's in one place and then you wait some period of time, it goes into smooth elliptical or circular shape, and then comes back at the end of that time period and is in the exact same spot it started in, so that it's guaranteed to repeat itself over and over again. So there's only two forces that can do that, 1/r². The other one's Hooke's law, which is force equals k times x, and that creates a stable orbit as well. And Newton went farther and was able to show that it actually those things can only create orbits that are conic sections. So what is a conic section? I'm going to draw that for you now. So if you know those little gas station water cups that you run into all the time, that's a good example to help us with a conic section. So let's imagine two of those as opposed to one of those, and they're touching tip to tip like this. And not only that, they're also infinitely large. So this goes on for infinity. Whoa. This goes on for infinity that way and the other way, and this goes on for infinity that way and the other way. Now, if I were to take this cone situation and slice it perpendicular to its axis, so imagine this axis goes right through the center, and it's a symmetry axis. So you can imagine it's going to be dead center right here like that, and it's going to come right through and be dead center right here like that. Okay. Now, if I take and make a slice of that exactly of the cone exactly perpendicular to that, and let's say on the top cone, then I'll make this shape right here, which looks like an oval or an ellipse, but in fact, that's only because I'm drawing a three-dimensional object in 2 dimensions. It's actually a circle. Dang it. Now, if I slice again, but this time I don't worry about it being perpendicular, or excuse me, I don't worry about it being perpendicular to the symmetry axis. I'm going to have it at a slight angle to the symmetry axis. Then what happens is I get this shape, which also looks a little elliptical or oval, but that in this case, it really is. So this is an ellipse. And that's really the only two closed orbits, is either an ellipse or a circle. And in fact, the lowest speed that you can go to put it into orbit results in an elliptical orbit. And if you speed it up a little bit more, a little bit more, a little bit more, it'll become a circular orbit. And then if you continue to speed it up, it'll turn back into an elliptical orbit, elliptical orbit, elliptical orbit, until you give it the escape velocity, at which time it becomes a parabolic orbit. If you give it more than the escape velocity, it'll become a hyperbolic orbit. So now, if you want to know what a parabolic orbit is, you can imagine slicing now parallel to the axis. So if I slice parallel to the axis of symmetry, then what's going to happen is you'll get a shape like this, and that's called a parabola. Now, if you decide to slice, let's say, that actually should be, if that's parallel, we'll go ahead and actually, I'm going to change that. I'm not going to make that a parabola. I'm going to do this. And it's technically probably not even right to call it a parabola, to be honest with you. So let me correct that. by slicing it that way, you can tell I'm actually going to end up having two pieces. Whoa, Nelly. He didn't want to do that. You're actually going to have two pieces. You can see that I'll have one piece over here down at the bottom, and then I'll have another piece up at the top like this. Okay. That two pieces you probably recognize from college algebra as a hyperbola. So that's what happens when you slice parallel. But if you slice instead, let's say you slice not perpendicular and not parallel to the curve, but you also don't want to hit something else, then that shape would do something like this. And that shape is a parabola. So those are your conic sections. And I just wanted you to understand what that meant, just in case you'd run into that word before in algebra and no one ever explained it to you. But that's sort of the idea of the conic section. This one kind of stunk. I don't like how that turned out at all, but I think you understand good enough what I'm talking about. Anybody have any questions on that? Okay, so as I was telling you, Newton was able to show that the only forces in nature that could create closed orbits were the F equals K times X force and the 1 over R squared force, which is what gravity is. And what I showed you just now was the 1 over R squared force or actually I just showed you all the possible shapes of trajectories that came from those types of forces. And those shapes are, of course, what I said was conic sections. Oops, wrong color there. That force that I said was in fact conic sections like this. Okay. Now that explains the first part. That explains Kepler's first law. Now, ultimately, what was used to explain the second law is something basically we now recognize as angular momentum. And it turns out that angular momentum is conserved whenever there's no net torque on the system. And that's why the second law is true. So you can say angular momentum conserved. And that's basically one way you could you could show that there's a mathematical or physical reason for the planets to speed up when they're closer to the sun and to slow down when they're farther from the sun. And then you could also use conservation of energy, and that actually gives you the equivalent of Kepler's third law. So this one you can sort of say is conservation of energy. That's one way you could do it. There's another way too, and that's what I'm going to show you now. Let's assume for simplicity that it's elliptical, that it's a circular orbit. And we know then what the acceleration of a circular orbit is. We have Newton's second law. And actually, let me put from over here too. Okay, we have Newton's second law, which says the total force acting on a body is equal to mass times the body's acceleration. And if something's going to go in a circle, that means that force, which we know is gravity, is going to be G times the mass of the sun times the mass of the planet divided by the distance between them squared. And that's got to equal mass times acceleration. But if it's in a circle, the acceleration has to be v squared over r. So with this, you can automatically see that the m cancels out, that one of these r's cancel out. But you can also go a little further and realize that we now have g times the mass of the sun over r is equal to 2 pi r over t, that's got to be the velocity, because if it's going in a circle, and it does go in a circle, and when it does so, it does it at a constant speed, and that means that speed has to be the circumference divided by the period. So that's what I've done here, but of course that has to be squared, and then you can go ahead and solve this, and what you get is t squared is equal to 4 pi squared over g times the mass of the sun times r cubed. So we basically have something that's exactly equivalent to Kepler's third law. And it tells us not only that, what if we had a planet or a star being orbited by a different planet other than one of our own? How would we find out how the period and the semi-major axis are related? Well, you could use this formula, and you just substitute the mass of the new star in that, and that'll give it to you. In fact, if the planet becomes appreciable in angular momentum or appreciable in size to the actual sun, then you ultimately have to find the center of mass of the system and then calculate the forces on it, and you'll get an equivalent law. But down in the bottom, instead of it being just g times the mass of the star, it'll be g times the sum of the masses, the mass of the star plus the mass of the planet. And in that case, the two objects are both orbiting the center of mass of their system, so that they're always on opposite sides of the center of mass, but they have equal periods. That's what happens when we have binary stars, stuff of that sort. And you can also show, which I'll allow you to do for extra credit, you can show that 4 pi squared over gm star is equal to about 1.0 seconds, or excuse me, years squared per astronomical unit cubed. Okay. And you can tell, obviously, that must be the case, because we know, for instance, for planet Earth, this equation applies. And how many years does the Earth take to make complete one orbit? It takes 1 year, so its period is 1 year. And in fact, the astronomical unit, the AU I wrote there, is the average distance between the Earth and the sun. And that, of course, is 1. So if you got 1 squared on one side and 1 cubed on the other, the constant that relates to them must be 1. So that's how we know that answer is going to be true. But what I'm asking you to do in the extra credit is go ahead and use 4 and pi squared and g and m. But the 4 and pi squared, they're not units. They don't have units. They're non-denominate numbers, so you don't have to deal with them. But you do have to deal with the g and the m and convert it to something that turns out to be ultimately years squared per semi-major axis, or per astronomical unit cubed. When you do that conversion, once you work out all the unit details, you will actually get 1. So any questions on that? So that's another way that you could actually show that Kepler's laws were true. Now, let me work an example. The first example I'm going to work is, we're going to imagine that I have a mass here and another mass. Actually, I'd really like to just copy that. Let's see if I can do it. Nope, looks like it's just giving me the chance to add a comment. Okay, oh well. I'll put another mass here. And what I'm going to say is, let's imagine these two guys are a distance of, dang it, are a distance of 2r apart. And then at, let's say 1R, there's another line this way that actually is 2R. And in this case, we have a mass. Dang it. In this case, we have a mass this big. Okay. These little masses are both the same. Lowercase m. I'll call this one MT for top, and I'll call this one MB for bottom. And then this guy over here has a mass of big M. And what I want to do is calculate the total gravitational force on M. So that's what we're going to do. So solution, remember Newton's law of gravity is what we're applying here. And Newton's law says that the force, there will exist a force of attraction between any two objects that have mass. That force of attraction is directly proportional to the product of the masses and inversely proportional to the square of the distance between them. And he found that it acts along a line connecting the center of masses of the two masses, and that R is the actual distance between the two center masses. Okay. So what that tells us is Fm, which means the total force on big M, is equal to Fm due to Mt plus Fm due to Mb. So all I've got to do is find those forces. Newton's law gives us a formula for calculating the magnitude, and it gives us sentences for calculating for determining the direction. So let's start off by just calculating the magnitude. So the force on M due to Mt is going to be G times big M times little m divided by, now we can look and see that the distance between them is that diagonal right there. And I think you can see that that should be the square root of, actually, let me take it off that thing. The square root of R squared plus 2R squared, like that, which I think you can tell that becomes R squared plus 4R squared, which would be 5R squared. So it ultimately becomes the square root of 5 times R. So I can now say this is going to be 5. Oops. I can now say this is going to be 5R, because obviously the distance has to be squared, even though I neglected to write the square down there. So does everybody agree that that's the magnitude of the force between M and M top? Anybody have any problems with that? So not only is that the case, but that means the force on M should be represented by this black line I'm drawing right here. And it's attractive, so it has to point towards the other mass. And I'm going to say this angle right here is theta. And I can use that to realize that the X component of this force would be right about here. And then the Y component of that force is going to be right about here, like that. Somebody else is coming in. So I've got all that. We'll deal with that theta and stuff a little bit later. Now let's look at the force on M due to M at the bottom. Now, there's a lot of symmetry between these two problems. So can anybody tell me what you think the magnitude of this new force will be?
2 cosine theta over 5r squared.
You're actually going ahead a few steps. But it does sound like you read it right, which is mainly that these two forces are actually going to have the exact same magnitude. I was supposed to put a big B there. I didn't do that. So let's fix that real quick. So yes, this one will be GM over 5R as well. And in fact, this one's going to have a X component this way, but it's also going to have a negative Y component for this one. So I'll draw it red there because the force is actually going to be, the force is actually going to be along this line again. And by symmetry, it has the same angle theta. I think y'all can see that now and see that the green Y component and the red Y component have the same size, even though they're not drawn to the same size, but have opposite magnitudes. So the net force is in fact going to all be to the left. There's not going to be any vertical component of force. And in fact, the horizontal component would just be cosine theta times the magnitude of the force. So this little part right here will be FMB times cosine theta. Now we can determine theta. We can say theta is equal to the tangent inverse of R over 2R, which is of course 1/2. And that's equal to 26.56, if I remember correctly. Let me double check on that. Arctan 0.5, 26.57 technically. But I'm not going to use that because I can be a little bit smarter than that. Now you see that both of them will have the same the same X component, so they'll add, but they'll both have the same Y component, just one will be positive and negative. So they add to give you 0. So that means the total force, Fm, notice I put a vector symbol on it, is going to be 2 times GM over 5R times the cosine of theta. And that's all going to be in the negative I hat direction based on these coordinate systems, where I'm going to assume this is the positive X direction and this is the positive Y direction. Okay, but I can make that a little simpler by writing negative 2/5 GM over 5. I really feel like that's supposed to be R squared down there. It's got to be R squared down there. Oh yeah, all of those should be R squared. Make sure you make that correction. Everybody see the R down there? I squared it, and I squared the square root of 5, but I evidently forgot to square the square root of R, or the square of the R. So in this case, I've already carried the 5 out in front, so all I have down here is R squared. But now I could take the cosine of 26.57 and put that number next to it, but I don't want to do that. I want to keep it nice and pure in terms of R's and all that good stuff. So I can look at the triangle and see that cosine theta would in fact be 2R. God darn it. Would in fact be 2R over, remember it's adjacent over hypotenuse. The adjacent side is 2R. The hypotenuse is the square root of 5 times R. And then all that'll be I hat times I hat, I should say. So I'm going to finally say that Fm, the total force on M, is going to be negative 4 over 5 root 5 times G M over R squared. Noticing, of course, that these r's canceled out, and all of that, of course, would be times I hat. Anybody have any questions on that? All right. So that's just another instance where you can basically create a vector out of a magnitude just by understanding the definition of the Newton gravitational force, specifically that the gravitational force is always attractive and acts along the line connecting the center of mass of the two objects. Your book even talks a little bit about how Newton realized that spherical shells would act just like a point particle with all of its mass at the center of that spherical shell. The only difference being that if you're inside the spherical shell, you're not going to get any gravitational force, but outside of it, it's still going to act just like it's a point particle with the same mass at the origin. So with that in mind, you can see that all I have to do is go from the center of the M, the little m, and the center of the big M, and everything works out. So still no questions before we move on? All right, so let me show you another question that occasionally pops up. Let's say if the semi-major axis of Jupiter is 788.3 times 10 to the 9th meters. What is its period of orbit? Okay. Solution. This is a Kepler's third law problem. And Kepler's third law says the square of the period is equal to 4 pi squared over g times the mass of the sun times the semi-major axis cubed. So I can say that t is going to be the square root of all this stuff that I just wrote. So I'm going to write 4 times 3.14159. That's just the way I write pi. You don't necessarily need that many sig figs, clearly. Now I'm going to take 788.3 times 10 to the 9 meters, and I got to cube that. Now I've got to divide all this by 6.67 times 10 to the negative 11 newtons meters squared per kilogram squared times the mass of the sun, which is 1.989 times 10 to the 30th kilograms. Now remember, a Newton is equal to 1 kilogram meter per second squared. So when I multiply this kilogram by the kilogram squared in the bottom, that kilogram is going to cancel out one of those and leave me a kilogram. When I take this cubic meter, this semi-major axis, and cube it, that's going to make m cubed, and that m cubed is going to cancel out both of these m2 or both of these m's in the bottom and leave a m up top. So now I've got a meter up top and a Newton divided by a kilogram in the bottom. Well, a Newton divided by a kilogram is a meter per second squared, and therefore I ultimately have that the units inside of this square root is just seconds squared because the meters cancel out. So this does actually give me the right units. Now I'm going to check that number. I think I recall what it's supposed to be. So that should keep me from making a careless mistake. That's got to be squared. So I just put in pi. I'm going to square that. And then I'm going to say 788.3 e to the 9. That's going to be raised to the third power. And then I'm going to divide this by parentheses 6.67 e to the negative 11 times 1.989 e to the 30, close parentheses. And I obviously made a typo because it's gave me an error code and I don't see the typo. So let me do it again. This time I'll actually include my square root so I don't forget it like I did last time. So 4 times 3.14159 squared times 788.3 e to the 9. And I'm going to raise that to the third power. And then I'm going to divide that by parenthesis 6.67 e to the negative 11 times 1.989 e to the 30, close parenthesis again. And that gives me a number that I did not recognize. 1, 2, 3, 4, 5, 6, 7, 8. I thought I got a 3.74 last time. This looks like I'm getting a 3.81. Anybody can confirm or deny anything that I'm saying here? I'm getting 3.818 times 10 to the 8th seconds. Yeah, that's too big. I'm wondering if I misremembered something. Let me look up real quick and just make sure I remembered the semi-major axis of Jupiter good enough. Can't believe I spelled Jupiter with 2 P's. What was I thinking? Anyways. Yeah, 7. So Jupiter has a semi-major axis of 778.4 is what this is saying instead of 788. And that's times 10 to the 9th, so 778. So maybe that's my difference. I'll say actually it's 0.5 technically times 10 to the 9th meters. So now let me try that. What I'm going to do is I'm going to take the 3818 that I had before, and I'm going to multiply it by the real number, which should be 778.4, or excuse me, 0.5 e to the 9. Oh, I need a square root in this. Hold on. 778.5 e to the 9 divided by 788.3 e to the 9, close parentheses, and yeah, that gives me a better answer. So I'm now going to use this red marker to say nope, and I'm going to use the red marker to say 3.794 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8 seconds. Now there's a neat little conversion that I use, and you might find it helpful too. And basically it means pi times 10 to the 7th is approximately equal to the number of seconds in a year. Okay, so that's a useful thing, and that's actually probably plenty good enough for us in this particular one. So I'm going to say t is approximately equal to 3.794 times 10 to the 8th seconds times 1 year over 3.14. It's actually, by the way, this number, if you work it out, it comes out to like 3.1555704, I think, times 10 to the 7th. So it's not exactly 3.14, but I think this is close enough using it. So I'll say 3.14 times 10 to the 7th seconds, and this will give me that gave me a little bit bigger than I expected. It gave me 12.08. Let me try it with the actual, well, I'll leave it like this, 12.08 years. Okay, if I actually did it with the proper number, 3.794 times 10 to the 8th seconds times 1 year over, now I'm actually going to do the math. Now the math is 365.25. That's the number of days per year. So 365.25 times 24 hours per day times 3,600 seconds per hour gives me 3.15576 times 10 to the 7th seconds. So this time I'm going to take that number, 379419832. I'm going to divide that by the answer I just got, and that still doesn't do much better. That only gives me 12.02. That's kind of a bummer. But anyways, 12.02 years. Both of those are really close. And really, to be honest with you, I don't think this is any better than 2 sig figs. Mainly, let me put a line through this. Mainly, it's only good to 2 sig figs. I know the answer is 11.86 years to 4 sig figs. So that's pretty good. It's good enough to 2 sig figs anyways. And I was a little rough on my 3rd sig fig. Specifically, I used 6.67. I could have used another digit. That would have helped. But that's pretty much it. So now let's try another question. We're going to do exactly the opposite. And specifically, we're going to say, if the planet Jupiter has an orbital period of 11.86 years, what is the average distance between the sun and Jupiter? Okay, so that's a pretty decent question. We're going to do the same thing again. I'll do solution. And what we're going to use is t squared is equal to 4 pi squared over g m s cubed. And that's going to tell me S cubed is equal to G times the mass of the sun over 4 pi squared times T squared. So I'm going to use that, and I'm going to do 11.86 years times 1 year is equal to 3.15, let's say 156 times 10 to the 7th seconds. So 3.156 e to the 7 times 11.86. That gives me that gives me 3.743 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8 seconds. So now I can say S is equal to the cube root of, now I'm going to say 6.67 times 10 to the negative 11. I've already worked out the units, so I don't care too much about them right now. The mass of the sun, 1.989 times 10 to the 30. And then the square of the period, 3.743 times 10 to the 8th squared. All that is going to be divided by 4 times 3.14159 squared. And then, of course, I'm taking the cube root of all that. This should give it to me in actual meters. So let's check that out. So 6.6, oh, actually, let me start with a square root, or cube root. Show the cube root key on this one. Actually, I can just use it to the 1/3 power. That's what I'll do. I'll say parenthesis 6.67 e to the negative 11 times 1.989 e to the 30 times 3.743 e to the 8. And now I'm going to square that. And then I'm going to divide all this by parenthesis 4 times 3.14159. I've got 4 pi squared under there. That closed the parentheses, and now I'm going to close the parentheses for the exponent, and I'm going to raise it to the parenthesis 1 divided by 3 power. And that gave me 7.78 times 10 to the, whoa, nearly. 7.78 times 10 to the 11 meters, which I think you can see is 778 times 10 to the 9 meters, which is a good check because that's what I ended up using before, once I looked it up and corrected it. Any questions on that? All right, so that's pretty much everything you could possibly imagine. Your book does talk about Lagrange points. It's a very interesting one. It does an example on it. That's where SOHO is, the Solar Heliospheric Observatory. It's at our L1 Lagrange point, which means it's sort of, well, it's about 1.6 times 10 to the 6 kilometers from our Earth, but it's along the line from the center of the Earth to the center of the sun. And it stays there in that orbit with the same period as us. So it's always got a clear view of the sun and a clear view of us. So that's one of the Lagrange points. And the Lagrange points are just neat points that a guy by the name of Lagrange found, where, for instance, you could make certain gravitational forces cancel out, and you could put something there more or less for free. And if I remember correctly, it's almost like 9 of them or something. But like, there's one ahead of us in our orbit. There's another one behind us in our orbit. There's another one that's further out and behind us in that sense. All sorts of stuff. So your book talks about that. It also talks about geosynchronous orbits. That's when you put a satellite, for instance, in orbit over the Earth, and you make sure that its orbital period is, 24 hours, or actually technically 23 hours and 56 minutes. If you want a sidereal day, if you want a solar day where it's going to be actually, yeah, that you really should use 23 hours, 56 minutes, to be honest with you. But anyways, if you do that, what you'll find is for that geosynchronous orbit, the actual satellite has to be about 6 Earth radii above the Earth's surface, or about 7 Earth radii from the center of the Earth. So those are neat little calculations you can do. They're all really fairly trivial. It's just a matter of setting up like I did here, where I put in, where I did here, where I put GMM over R squared is equal to MV squared over R. So this whole part right here is something that you should be able to use. Any questions on that? All right, so let's start chapter 7. And what I'm going to give you is next time I'll do a few derivations and I'll do a little bit more explanation. But what I want you to know right now is there's a potential energy. U equals potential energy. And there's a couple different ways you can do it, but if you assume that you're going to be close to the Earth's surface, where your distance away from the Earth's surface is considerably less than the radius of the Earth, then you can say that the potential energy, the energy that you have to do work potentially, is given by the mass of U times G times essentially an arbitrary H. What I mean by that is it's arbitrary what you consider the zero height to be. But once you choose that zero height, just stick to it and everything will work out fine. An example would be like if I'm in the upstairs of a building, I might say the height is of this object, which is slightly higher than my head, is 2 meters. But someone downstairs might say that's 5 meters because it's 5 meters above their floor. Both of us can work the problem, that person using the 5 meters and me using the 2 meters, and we'll both get the right answer. But if we're looking for the final height, we have to correct by a difference of 3 meters. So long as we stay inside of our coordinate system where we chose H equal to 0 to be a very specific point, it'll work out. Later, we'll learn when you're at distances that are comparable to the radius of the Earth, then there's a more complex potential energy formula. The unit, by the way, of energy, which includes, of course, potential energy and all these other types of energy I'm talking about, is the Newton times the meter, which we define as the joule. Okay, so that's another thing. There's also a quantity called kinetic energy. And Madame du Châtelet, the beautiful young 16-year-old girl that translated Newton's Principia, like I said, at like the age of 16 or 17, she called it oomph. She's French, so you gotta say oomph, but she called it oomph. And in classical physics, it's 1/2 the mass of the object times the square of its velocity. There also happens to be a potential energy that you could have stored in a spring. So if you either put a mass on the spring and you stretch that spring by an amount X, or you compress it by an amount X, then the energy stored in it is a type of potential energy, and it's given by 1/2 kx squared. There also happens to be another form of kinetic energy that we will eventually get into, and that's the kinetic energy of rotation, and that's 1/2 I omega squared, where this is called your moment of inertia. It's sort of your reluctance to rotate. And it goes like the product of your mass times the square of the distance of that mass is away from the rotational axis. So you can do calculus to calculate it. This omega is an angular speed, which you might say is RPMs or radians per second or something like that. We're not going to be using that in this chapter or the next. We're not going to use it until I believe it's chapter 10 where we do rotational motion. But I just wanted to give you a feel for what those are and tell you that we're going to derive them later. But now that you have this, there's only one other thing you really want to look at, and that is work, which technically becomes the integral of F dot dl, meaning what you want is the component of the force that's parallel to the motion. That's why the dot product's in there. And what you want to do is for each little section of the trip that you're pushing this thing through, you want to take the appropriate force and the component parallel to the motion and multiply it by that little bit of motion. And then when the force changes, you're going to have to change the force, multiply it by the next bit of motion. And if it changes again, do it again. In general, though, if the force is a constant and parallel to its to the motion that you're pushing it along, then it's just F times X. So that happens to be another thing, as you can tell, would have units of newtons times meters, because DL should be meters and F should be newtons. So this actually comes out in joules too. Now, what I want to tell you is that, oh crap, we're running out of time. Let me give you this last equation. The equation I use is U initial plus kinetic energy initial plus work in is equal to U final plus kinetic energy final plus E loss. That could be like work done against friction plus work out. That could be like compressing a spring. Work in could be like compressing a spring, or it could be someone applying a force to it. I will let you look on my YouTube channel for videos of us using this, but we're done now because the time's up. It's 2 minutes after 6:40, so I guess our time's up. But I wanted to make sure I at least gave you that. You folks have a good one. I will wait for the last person to leave in case anybody has any questions. Thanks for coming. Josh or Adam, anybody have any questions? Devon, Devion.
All good.
Thank you, Professor.
You're welcome. Thank you.
Too.
All right, I'm going to stop sharing then. It looks like everybody's left. All right. We'll show you an example using that later, but you can also see them in my YouTube channel videos. Have a good one.